Hello everyone, my name is Nader, and in this video I will present our recent transaction of computers paper called Remote. Remote proposes a robust and external malware detection framework that can be used for detecting malicious activity on resource-constrained devices by leveraging analog domain side channel signals such as electromagnetic signals. This work has been done with my colleagues and collaborators at Georgia Tech. So first of all, let me give you a little background about side channels. So side channels are unintentional byproduct of the computation. There are many different types of side channels, including analog-based side channels and digital-based side channels. And it is very well known that side channels can leak sensitive information about the system, mainly because there exists an existing correlation between these signals and the critical information being used in the system. Knowing this existing correlation, an interesting question is, can we actually use this external source of information for other useful purposes? And the main idea that we propose in this paper is that we can actually use side channels for benign purposes, such as profiling or debugging, monitoring, integrity measurements, and so on. Our main focus in this paper is actually on malware detection. That we can use the signals for doing the malware detection and detecting anomalies in execution of a system. So the main advantage of using side channels for security is that these type of methodology actually does not incur any overhead to the system. Moreover, it's physically separated from the system. And more importantly, they have no observer effect on the system, which means that in no ways they actually change the system. Which means that given these three main advantages, they are particularly useful for cases such as IoT devices and resource-constrained devices in general, where you essentially doesn't have enough resources in order to run a sophisticated security mechanism. So in this work, we're particularly using electromagnetic side channels as a source of information. EM side channels are generally created unintentionally due to the switching activity of transistors. The main advantage of EM side channels is that they can be measured from this distance, while they have no overheads no overhead on the system itself. And then using this idea and using the signals, we are creating this framework that collects these EM side channel signals and create and builds a reference model based on that, and that represent the correct execution model of the system. Once this model is built, then it constantly monitors the system and compares the newly generated signal to the model. So if there is a significant deviation from this existing model, then the model actually reports it as possible anomaly and stop the execution of the program on the system in order to detect the malware. So I encourage you to read the paper to learn more about each of these steps and how we actually do the signal analysis in the frequency domain, how we do the clustering and do the training, and then how we actually do the monitoring in order to detect these malwares. So in this video and in the paper itself, we actually, in order to evaluate how well this framework works, we tested our method on a medical cyber-physical system called syringe pump. Syringe pump is a medical device used to inject or withdraw a specific amount of medicine, and is a great example of critical cyber-physical system actually used in the market. We implemented a classic buffer for overflow attack on the system, where an attacker can move the syringe into an arbitrary direction by corrupting the stack and hijacking the control flow, as you can see on the image on the right of this slide. Now in this part, I want to show you how the system works and how the malware can be detected based on this framework that we have created. This is the syringe pump, which has a syringe which is connected to a DC motor, and the DC motor is connected to a controller, an Arduino in this case. The signal will pick up using this probe, and the signal is connected to this software-defined radio, which sends the commands to the computer. There's also a feedback loop from the computer, which connects to the power of the system, and as we detect an anomaly, we can actually automatically shut down the power of the system. So in this figure on the left, I'm showing how the signal looks like in the frequency domain of this syringe pump, and on the right I'm showing the command, the terminal that we are sending and receiving some command. So now let's send the command to move the syringe into the to withdrawing some signal. As you can see, once the command is sent, you see two different signatures corresponding to first checking the command and then second to actually move the syringe, as you can see in this figure on the left. Now let's start the attack by doing the buffer overflow. And then we are sending a command followed by the return address of the moving the syringe. So as you can see, once the command has been sent, the syringe immediately start to move, and this time the signatures actually looks different than what is it was before in the actual commands in the actual execution, which is how we actually detect it. So in this part, I'm going to show you how our detection framework works. As you can see, it's implemented on MATLAB. And now we are actually start to doing the monitoring. This time I'm gonna send the command, and then as you see, immediately after the command is sent, given that the signal are different from what it was supposed to be, we immediately stop the execution of the malware. We shut down the power and send an error message that the malware has been detected. So this is actually how the entire thing works. We essentially use an antenna to pick up the EM signals, and as we do the monitoring with the EM signals, we constantly compare the signal to a reference model, and then once we detect a deviation between the signal and the reference model, as I showed in the previous slide, we report it as a possible anomaly. In this case, we send the command to shut down the power, which immediately stops the movement of the syringe. So with that, I want to thank you everyone for watching this video. I encourage all of you to read the paper to learn about this work and our previous work in this domain as well. And if you have any question, please send me an email and I'll be happy to answer some of the questions that you have. Thank you.